Damit hätten wir den Bereich I/O für Cyber Physical Systems, sag ich mal, abgehakt. Was mich jetzt eben nochmal interessiert, sind die Datenquellen, die dort dahinter stehen. Was könnt ihr mir dazu sagen?
Ja, das ist ein Bereich, wo ich gerne eine Kollegin von mir auf die Bühne bitten würde, die sich eingehend mit diesem Thema auseinandergesetzt hat. Please welcome Kamalina, Srikant.
Well, hello Kamalina.
Hello, Daniel.
So,
Bonjour, mesdames et messieurs.
So you've been working very close with our customers on some of the most complex cyber-physical systems, and you've been doing a lot of research there. And so tell us, what is our NI's perspective on these systems, and especially the data sources behind them?
Okay. Well, one of the most interesting things about these applications, like the structural test example we talked about earlier, is the amount of data that they generate. Let me give you a concrete example. So phaser measurement units that are deployed in the smart grid generate up to 5 terabytes of data per month.
Wow, that is a lot of data.
Well, it gets even bigger than that. I'll talk about some other applications that our customers are involved in. For example, factory acceptance tests for turbines are generating around 10 terabytes per day. But it gets even bigger than that too. Jet engines that are flying while they're in flight, we can be measuring up to 20 terabytes per hour. But all of that is minuscule compared to the amount of data generated right here in Switzerland, 40 terabytes per second at the CERN Large Hadron Collider.
Well, that is sure what they call big data, right?
It sure is. But usually in the media, when you hear about big data, they talk about things like number of tweets, number of Facebook likes, or metrics around sales transactions and revenue. But what we're talking about here and that all these applications have in common is big analog data. And as you know, or as I'm going to tell you, big analog data sources are older. They've been around since the beginning of the universe. They're faster. We require very high rates to be able to measure these phenomena. And they're bigger. It's constantly being generated around us. And many of our customers are building systems and solutions that are generating lots of data.
Okay, so how can we as an I help our customers to acquire, analyze, and present this data?
Well, to answer that question, let's take a look at how the data flows through a big analog data end-to-end solution architecture. So first, there are sensors that measure analog phenomena from a variety of sources, such as assets that are under operation or devices that are under test. And this data will then flow to acquisition and analysis nodes, such as NI's Compact Rio, PXI, or Compact DAC systems, where preliminary processing can occur and the data is, in essence, acquired and digitized. But then the data will get passed on to traditional IT infrastructure, where it's aggregated with other sources and more in-depth processing can occur, and then onto corporate enterprise data centers, where engineering insight will be turned into business insight and decisions can be made.
Okay, so if we have a look at this, what is the actual value for our customers in there?
Well, the thing is that I'll talk about some investments that we're making into these technologies as well, and then I'll answer your question. So one of the things is that as the amount of data grows and as the number of systems increases, things like data management, data analysis, and the management of these system nodes become key considerations. Okay. And NI is investing in these software technologies to address these considerations, but also making investments in our partnerships with sensor, IT, and integration companies. And that, along with the openness of our platform, helps to promote interoperability between these three tiers. Now, that being said, these investments that NI is making in the platform and in the partnerships are essentially helping our customers to reduce integration risk and decrease time to value so that this business insight can be derived sooner.
Very good. So can you give us a quick example?
Sure. This morning we heard about Duke Energy that Alex Davern mentioned, so I'll talk about them really briefly. They're the largest power generation company in North America, and they're doing fleet-wide monitoring of all of their rotating equipment and assets. And they're doing this in order to improve their operations and maintenance processes, to decrease the risk and the maintenance costs, and to increase the reliability and the yield of the electricity that they're providing to the grid. And they're using NI technology to monitor tens of thousands of different assets using over 30,000 different types of, well, different sensors of varied types. And there can be up to 200 or several hundred Compact Rio systems located at each plant, and each plant has a server running on it, server running there that's running NI software that is taking care of the data management, analysis, and the management of the compact Rio system nodes and the alarms. This data, the results are calculated, and metrics are found, and then it's relayed to corporate monitoring and diagnostic center. And at this corporate monitoring and diagnostic center is where advanced pattern recognition is being performed, faults are being identified, and work orders are being generated. And that's how they're getting their business insight. And this really is a big analog data solution, as you can see.
Absolutely. Well, thank you, Kamalina, for sharing that insight. And what I would like to do next is bring a big analog data solution up on the stage that we have right here in Switzerland. So to do this, I would like to call to the stage Mr. Dr. Thomas Blum from the ETH Zurich. Thank you, Kamalina.
Thank you, Daniel.
Hello, Dr. Blum.
Hi.
So tell us a little bit about your project.
Sure. So I would like to point out that it's a major project for my group at the Institute of Geophysics at ETH, and it's still ongoing. So what we're trying to do is build a lab to look at wave propagation. And so we have a big water tank where we would like to put samples, say a piece of rock, in order to look at its mechanical properties. And so there's nothing new here. It's been done in other groups already. But one of the drawbacks of using a big water tank like this is that its size is still limited physically. And so when we look at wave propagation, we end up getting reflections from the sides of the tank that interact with the actual waves we're interested in. And so this prevents us from doing further characterization. And so the innovative part of our project is that in order to overcome this, we are using what are called exact boundary conditions in order to tie the physical part of the lab with a numerical model that is running at the same time. And so what you can see on the screen is that in order to do this, we have to measure the wave field just before the boundaries of the tank. And then we use this to predict what is actually going to be at the edge of the tank. We process this data, we run it together with a numerical model, and then we re-inject extra acoustic energy at the edge with actuators in order to tie the numerical and the physical part together. And what it basically ends up doing is canceling what you would get as reverberations from the edge in order to get a bigger physical domain and state.
Okay, so to put it in a nutshell, you're basically simulating something like an earthquake and studying what the wave propagation is doing to a certain object of interest, right?
Uh-huh. Yeah.
Okay, so could you show us the implementation, or how are you approaching this?
Sure. So this is the implementation that we have in mind. So inside our physical space, which is the water tank I've been describing, we are going to have a recording surface with probably around 1,000 sensors. And those sensors are connected to system nodes, basically digitizing the data that we get. Then we tie this into some pre-processing units, and then some high-power computing that will do all the number crunching that we need. And then we re-inject this data through the emitting surface, which is actuators that are at the edges of the physical tank.
So basically we see the three components of a big analog data solution there, so very impressive. So tell us a little bit more about the benefits that you have seen in the cooperation with National Instruments.
Sure. So the benefits that we can see so far is that, first of all, we have integration of the different steps. As I was describing, we need to first digitize the signals, the analog signals that we're acquiring. Then we need to do some pre-processing, which is probably going to be done with FPGAs. And then we need to send this to a high-power computing system that does the number crunching. And all of this through NI is seamlessly tied together so that we have a continuous flow of data between those elements.
Well, surely a very interesting and powerful application that you have there. So thank you, Dr. Blum, for
Thanks.
bringing this to us. Thank you.